Good morning. Yeah, thank you very much. Thanks for everyone who's coming out after the conference dinner. Everyone is relaxed. huh? Um, so I'm in a bit of a weird situation because people asked me to talk about both laser cooling a little bit and then many-body physics. So let's see how we can fit this into 25 minutes. Um, so here's the outline. I will talk a little bit, like I said, about how we are laser cooling fairly complex molecules these days, mainly with the aim of using them for precision measurements. And then also some, I guess, theory work for now, addressing some of the questions that we had yesterday or that came up in the discussion yesterday about dipolar physics. Of course, there's plenty more talks about this in the whole conference about both of these topics. And oops, sorry. So how do I get this to point? Here we go. Like in this session, there will be some more talks about the laser cooling and the precision measurements as well. So let's start with the laser cooling. And I really stress this is about laser cooling complex molecules. So I need to tell you what complex means for me, actually. And for that, we need to look at the challenges of, wow, this is weird. The challenges of molecular laser cooling. And there's two, of course, main challenges, which you all know very well and which have been solved quite a while back. Vibrations, vibrational branching and rotational branching. You just have to pick the right molecule with the right electronic structure here, where you can talk to one electron in order to get rid of most of the vibrational branching, and then you use selection rules for getting rid of rotational branching. And this is, of course, very successful and basically the basis of everything you know about molecular laser cooling, starting from the initial experiments on strontium fluoride all the way now to fairly complex polyatomics even, and then many, many more species, as you've already heard. But then there's actually a third challenge, which is oftentimes not discussed so much or even avoided, and that is hyperfine complexity. And the reason it's mostly avoided is that in most experiments, the molecules look like this with only one nuclear spin, or alternatively, I think we will have some talks about molecules where the hyperfine structure is not resolved at all. And so there is actually not so much hyperfine complexity in these molecules. You usually get some kind of fairly regular splittings, and then you just apply some roughly suitable sidebands, and you will end up with sizable forces, and you can cool your molecule. What I'm more interested in this talk is a situation where you do actually get more nuclear spins, and then things do become more complicated, and in fact, they become much more challenging, as you will see, but they also become more promising in certain aspects. And the reason why people don't like this is that it usually leads to hyperfine structures like this with really many levels involved, where it's absolutely not obvious anymore how you would generate laser cooling forces. It's very promising though, because people have started to work with a bunch of species that are very promising for precision measurements and where laser cooling obviously would make a very big difference if you can actually cool them. So what kind of super promising precision measurements would that be? I mean, you all know the electron EDM searches that are ongoing, and these are of course very advanced experiments where the next generation will certainly rely on laser cooling. So I think there will be a talk in this session about that topic as well. So these require usually molecules with a heavy nucleus. So that's still fine. It's challenging because of the heavy mass, but the structure of these molecules is not yet a big deal. But then there are actually many more precision measurements that you can do with molecules. For example, searches for properties of the weak interaction, searching for an anapole moment of a nucleus. And for this, for example, there's just a proof of principle experiment so far, but no actual measurement. And the reason why there are no such measurements yet is because we don't have enough molecules, because preparing something that has a finite nuclear spin in a single quantum state is already an issue, and then laser cooling and accumulating it is even more so. Then you may have heard there's a lot of people now working with radioactive molecules at CERN, for example, or even in offline experiments now. And they are looking for basically CP violation somewhere inside the nucleus, so an EDM of the nucleus. And here, even in addition to also needing this finite nuclear spin, these molecules are going to be short-lived and come in low abundances. So if you want to do any of these experiments, and people do this with exactly the species that I've been mentioning so far, and it really requires this second nuclear spin, you You will have to realize the strongest possible forces and efficient detection. And for this, you need to optimize things. And if you want to really go into this field of nuclear physics here, then you really have to understand and exploit this hyperfine structure that is given to you by your molecule. And also a side note, because there are many body people here, also most laser coolable fermions will have that property. So if you want to make cold Fermi gases by laser cooling, this will also require you to deal with this hyperfine structure. Good, so the molecule that I like to work with and that 50% of the speakers in this session like to work with is barium fluoride. This is the most abundant barium fluoride, 138, but there's a whole series of other barium isotopes, and so you get a whole bunch of isotopologues that you can play with. These even ones here with an even number of neutrons, they are EDM candidates, and okay, you know the game, right? There's some electrons in these molecules, and they are experiencing a hugely enhanced effective electric field. Maybe not the absolute largest one in barium fluoride, but because this is still fairly simple molecule, you can hope to gain in your measurements just by laser cooling and trapping. And then, okay, this is fairly abundant and it's fairly simple because it just has this one single nuclear spin. But then, you will see this later. For us now, it's mainly a test case so that I can show you how you actually optimize laser cooling in complex systems. And then there are these odd isotopes or odd isotopologues, which are candidates for these anapole moment surges. And what you're really looking at is you want to build a sensor for the dynamics in the end of a valence nucleon. So this is not an electron anymore, but the nucleon that somehow orbits the nucleus. And you're probing the nuclear spin basically of the barium metal. And that gives you this complex structure. And why do you actually need this? Well, I told you in the beginning, you need this particular structure where one electron sits actually on the barium metal for laser cooling. And that electron is actually what you are probing in the end to probe the nuclear spin. So it needs to overlap essentially with this nuclear spin. So you cannot use these simple isotopes, you need the complex ones. And on top of that, you see the abundances here. We work with natural abundances. They're already an order of magnitude lower than for the most abundant isotope. And so it's a bit challenging. So there's a lot of things that we can talk about. In the interest of time, I'm actually going to skip the spectroscopy part. Ask me if you're interested about this. You can already see some nice nuclear physics in this by just doing king plot analysis of isotope shifts. And you see basically how the size of the nucleus of the barium actually becomes smaller if you add nucleons to it, which I guess is a bit of an odd behavior, and it has to do with nuclear correlations. But again, so if you're interested in that, just ask me afterwards. Let's start with the laser cooling to begin with. And so here's the laser, the level structure of these molecules. Looks fairly similar to most of the other laser coolable molecules that you may have seen, with one small difference. Something that came out of our spectroscopy was that in the excited state, the hyperfine structure is resolved. And that is different from the usual suspects like strontium fluoride or calcium fluoride. Let's imagine for a while, though, that this splitting would be zero. And then the spectrum would actually look something like this. And barium fluoride would be a very lucky molecule because you could just apply sidebands with a single sinusoidally driven AOM, and that would fit almost perfectly. And then you can calculate the forces by solving your optical Bloch equations, and you would get some sizable forces. So this is basically velocity and the size of the forces given by the color. You see there's a big blob here with sizable forces. Now, in reality, though, I go back one more time, so look at the spectrum. In reality, because of that splitting, some of these lines get slightly shifted, and you would think, okay, that is not going to change much, right? But now, your spectrum doesn't fit at all anymore. It's just a few megahertz, but that is already enough to basically completely destroy the forces in this molecule. So you have to know very well the hyperfine structure to actually be able to cool even these most abundant isotopologues. And so we can ask ourselves now, how can you make this better? So what do you need to apply to actually maximize the forces? If we can destroy them, we can also optimize them. And of course, there's a lot of parameters to play with. These calculations for optical Bloch equations, they do take a while. And so what we did was basically Bayesian optimization, which is like something that you can just get from Python in a package. And it's very well suited to optimize something that is computationally heavy. And then you can calculate forces, okay, and then as a function of parameter, at some point your algorithm finds something that looks nice and looks like a sizable force, and then you look at what kind of spectrum that actually corresponds to, and it suddenly corresponds to a spectrum that looks very different from the ones that we usually apply, because it doesn't have like sidebands that address all lines anymore, but it only has 3 lines here addressing 5 transitions. And that is very odd, but it seems to be better. So why is it better? Well, first of all, what you find is that this single line here, this that you apply, is actually the one that generates most of the force. And that actually you can understand because you're actually driving this transition here, which comes from an F equal to 2 ground state, which is the ground state with highest multiplicity. So this is where all your population spends most of the time in. And so this is actually where the forces come from. And the rest back here, you do not need to put a lot of power there. It's just for repumping such that your cycle is still closed. And then also you learn something about the general complexity here. Why is it just this single one and not 2 transitions that you drive here? Well, if you were to apply a 4th sideband, then you know that you have to red detune or blue detune to get cooling or heating. And in this doublet, so to say, if you're detuning one of the transitions one way, then you're always detuned in the wrong way for the other transition. So you're basically killing your forces with the second sideband that you're applying. And so it's much better to just have a single one. Good. Now, how do you generate some weird spectra like this one? The conventional method would, of course, be to make this a bit more elaborate, add some AOMs with your EOMs, and then in principle, you can generate almost everything, but you're still limited by the amplitudes, for example, are still given by Bessel functions and so on and so forth. The spacings are set by the drive that you put on there. And also, in terms of like experiments, in molecular laser cooling, you do need all the power you can get. And if you put something through EOMs and AOMs, you're just losing a lot of power. So that's not very efficient. So what is a better way? What we came up with is an old technique. It's not something new, Cerodynes. So in Cerodynes, what you do is you drive your phase modulating EOM not with a sine anymore, but you drive it with the sawtooth pattern. And then it's a fairly easy calculation to see that such a slope basically shifts your frequency of the laser by something that is proportional to the slope that you're applying in your sawtooth. And then you just concatenate different slopes, and so you're just looping through different frequencies. So this is basically the 4 frequencies that you see here, but you are very flexible now to do anything you want. And as long as you're looping fast enough, your molecules don't realize that the frequencies are actually not there all the time. So this gives you a very high degree of flexibility, and also, again, speaking in terms of lasers, it gives you very simple laser setups, because you can just fiber couple your initial seed laser, you go through fiber EOM, and then you just amplify. So no more free space optics at all. Good, so this is how the experimental setup looks like. You have a buffer gas source somewhere, usual setup, right? Then transverse laser cooling, where we're bouncing back and forth the lasers. And then at some point there's some experiments, and now you have to imagine basically any kind of precision measurement setup that you would like. For now, I will just show you pictures that have been taken of this molecular beam, because we want to characterize laser cooling. And we detect this with a very nice different way of building the optical cycle, which involves basically 2 cycles with Raman transitions, and then you have background-free detection. So this is one of the things, of course, you want for your precision measurements in the end. And so here's a picture the molecular beam. Okay, this is the reference, and then we apply cooling, and you see already that there's a huge enhancement here in the center, where we have enhanced the number of molecules in the coldest part of the distribution, so to say. This is a very collimated molecular beam now. If you were to do this in 2D, and we will hear about this in, I think, one of the next talks, this is already a very good resource for an EDM measurement. Yeah, okay, and then you can also do heating, so you believe me that we're really understanding the forces that we're applying here. Now, why does that work so well for such a, crappy molecule? It's very heavy, the forces are usually not so large, and indeed, if you're just applying this sinusoidal drive, you hardly see any cooling here. You're not even like enhancing your molecular beam, you're just losing from losses. But then as I pointed out before, you can optimize these forces, and we can like test this all in the experiment and apply something that is more like what the simulations were telling us here. And then you do start to see this peak, and you can even make this more efficient really by putting all the power that you have into this one important sideband here, and you see that is really what gives you the strong forces in the end that collimate your beam. Good. So bottom line is modeling and optimization work well. We know what we're doing in terms of these forces, so let's move on to something more complicated. And that is basically now working with the other isotopes, which are much more rare. And so this is sort of standard in atomic laser cooling, obviously, working with different isotopes, accumulating stuff, working with mixtures, trace gas analysis, you name it. But with molecules, this had not been done so much before. And so we're going to test this now first with the next even isotope, because this has the same level structure as before, so it's a nice thing to test this. And what is the problem? In general, these spectra are not like sharp lines anymore, but they have all these extra transitions, all this hyperfine structure. And so neighboring isotopes usually overlap. So if I were to just put a laser light on this transition here, which is the cooling transition for my rare isotope, I would see the photons of the more abundant isotope. So that doesn't work, right? But what you benefit from now is that you're actually building an optical cycle. And for the different repumping transitions here, the isotope shifts are actually different. And so now for the two isotopes, for the repumper, the transitions are very separate. And so the bottom line is, as long as you're building a cycle and you're scattering many photons, then you can make this very selective again. Works with any molecule and also with any kind of laser cooling technique that you can imagine. And so we can have our beam and we can now image both isotopes separately by just using two different ways of building the optical cycle. So one with this Raman scheme, the other one with a regular cycle, and then you see them independently. You can apply cooling to the rare isotope, which then, as you've seen, because of the spectral overlap, affects the more abundant isotope here and it disappears. But we know that it has just scattered one or two photons and gone into the first vibrational level, and we can just bring it back. And then we can see that the rare isotope can be cooled selectively. The other one remains completely unperturbed. If we want, we can also remove it. And the bottom line is I can prepare now arbitrary compositions with millisecond turnover time for isotope selective scattering, for example. If you think of a mod, you could also, I mean, if you just put on more lasers, you can create mixtures, whatever you like. Good, okay. So, but that now sets the scene for the cooling of the complex isotopologues, not just for buff, but also for other things beyond that. So how about these fermions? And I remind you again, these are now the ones that have this extra nuclear spin, which makes everything more complicated, but which also makes these isotopes sensitive for precision measurements of anapole moments, for example. And here's the level structure one more time. You see it really looks ugly. You don't have to do the counting for yourself. I will do it for you. There's 48 ground state levels and 16 excited states per vibrational state. So the cycle that we built, which involves one repumper for the experiments here, contains 112 levels, which I can always easily remember, because it makes you want to call the emergency hotline. So here's how the spectrum looks like. You see there's a lot of dirty overlap with other isotopologues, and then there's this super messy spectrum here. But we can basically just apply the principles that I've explained before. We put basically strong lines on the transitions with the strongest, with the highest multiplicity. This is going to give us our forces, and then we just apply some spectrum for the rest that doesn't overlap with what we do not want to talk to, like the other isotopologues. And then actually you can see, first of all, if you're just applying sidebands to some transitions, okay, there's a little bit of fluorescence, but if you close the cycle, then of course the fluorescence goes up. So you are closing the cycle. You have optical cycling in this system. You can then, based on this, have direct imaging of this rare isotopologues, despite there being a very, very strong overlap with other isotopologues. You know that it's just this because the cycle is closed. And then you can also laser cool and do all the tricks like this. So that is great. The question is, how far can these principles be pushed? First of all, we can apply this, of course, to simpler molecules, like we have an experiment on calcium fluoride also, which, as we discussed yesterday, you just need to improve a little bit all the steps to actually maybe push this into the collisional regime. And one thing we are looking at is just transverse cooling for now. And with these serodynes, actually you have new things that you can optimize, because not all the frequencies are there all the time. And the problem in transverse laser cooling and slowing of such a beam is that you're always competing, like the slowing is competing with the transverse directions for photons. But now you can actually apply serodynes in these two beams that just talk to some substates, and you're not competing anymore. So it actually works fairly efficient. One thing I did not mention was that the nuclear spin actually breaks also the rotational selection rule. And that is maybe the biggest downside of this nuclear spin, actually, because as you have seen with the complexity we can deal with now, so for barium fluoride, this is not a big problem. We can scatter 2000 photons. That's totally fine, as you have seen. But for other molecules that people are considering and are putting a lot of effort in, actually that basically kills the laser cooling. So radium fluoride, I think, is not going to work. Otherwise, I mean, you may need a lot of rotational cooling for sure. YBOH is also bad in that sense, and that suffers from inner shell excitation losses in YB, which I guess we will hear about for YBF as well. Just for context, if you say, okay, 2000 photons is not a lot, I was not mentioning that there's another loss channel in barium fluoride, but that one has already been fixed, and these losses actually go to sort of the same states. And so I'm very certain that this is not a showstopper for a barium fluoride fermionic mod. So this is what we're working on. In the end, if you do the counting, that would involve something like 750 levels, so almost 1,000. For the North American audiences, it's almost your emergency hotline. But so despite these problems and challenges, these principles and this intuition that you can build for laser cooling, I think it's straightforward to transfer to many, many of these complex species. That I would go so far to say there's almost nothing that you can't laser cool. You just have to come up with a very good reason, in the end, to go through all of this. Good conclusion. I was actually going to remove that slide, but because Lawrence was mentioning it yesterday, I just want to put it up again. So you all know atomic laser cooling, right? 2-level systems, that's a great thing for groundbreaking experiments. I guess molecular laser cooling becomes a little bit more challenging, but it's actually feasible for many species along very similar lines and strategies in principle. But now we really have to embrace the complexity of molecules because it can give us a lot of new tricks. There's new kinds of magneto-optical traps, for instance, that are really much better that you can't do with atoms. Also, the low background detection that you can build here, you cannot easily do this with atoms. So embrace the complexity. So I think I'm going to skip these conclusions. Okay, so what I've shown you is just going to be a very big game changer for precision measurements with the fermionic barium fluoride, orders of magnitude more signal, and we will learn about anapole moments hopefully soon. What I briefly want to mention is that you can push this also into this very fashionable radioactive molecule regime. There are some interesting isotopes of barium for this also, and then you can maybe even measure EDMs using these techniques in nuclei. Good. Now, I have 2 minutes left, so I have to be quite quick. Total change of gears. I'm putting my theorist hat on now. So dipolar physics with molecular BCs. I mean, we had a wonderful session yesterday, and this is, of course, what this is motivated for. You know that I have quite some, or had some interest in magnetic quantum gases, or at these meetings we call them mono atomic molecules, right? And this is pushing now towards real molecules, bigger dipoles. That's the selling point, of course. So the question I want to put out is like a bit of an outrageous question. Are the dipoles actually going to be strong enough? So let me explain what I mean by that. And for that, let me say, some of you also know that I'm interested in supersolids. What is a supersolid? It's something that is solid and superfluid at the same time. Was initially always investigated in helium. You know that helium can become superfluid if you cool it, and if you increase the pressure, it becomes a solid. And so the idea was always that you then end up with a helium crystal like this. There's some vacancies inside. The vacancies, if you just get cold enough, become mobile and abosonic. So this gives you some superfluid fraction, and then you have a supersolid, something that combines the crystalline structure and superfluid flow. The problem is there was initial evidence, but then it was later disproven. And so in helium, it's a tough game investigating this. Now, in magnetic quantum gases, we've investigated this question the other way around. Can a superfluid be a solid? And there were a lot of experiments. You can always recreate this like with simple ferrofluids. This is essentially the experiments that you've seen yesterday with molecules in a very basic fashion. There's some symmetry breaking, there's droplets forming, and so on. These droplets you can simulate on the mean field level very easily. So Lewis, for example, was one of the founding fathers of this. And then, okay, experiments reproduce this, and there's a lot of things that have been done both in our group in Stuttgart and in Francesca's group and in Pisa and Florence also. Supersolids do exist in that form where you have these droplets. And that's, of course, now something that everyone is looking for in molecules, because there's a lot of questions that you cannot answer with helium and you cannot answer them with magnetic gases. And like, for example, how do you actually check this theory? We were discussing yesterday, how do you go beyond mean field? And even on a more fundamental level, how do you connect these two very distinct pictures of something with a perfect crystal where like vacancies are flying around and giving you superfluid properties, and droplet supersolids? So helium and magnetic atoms. And it turns out sort of dipolar molecules should be able to interpolate between these limits. And the first evidence came from mean field simulations that we did like 2 years ago, where you could see that the density in these droplets, if you make the dipoles really, really large, they tend to go to this single particle limit that you have in helium. Okay, that is obviously a limit where mean field simulations are not working anymore. So we had to switch basically to Monte Carlo simulations. And this is actually reproducing this. So these are now crystals that form where every blob here is a single molecule. I promise I will be quick. and first of all, this is very interesting from a fundamental point of view, because this is now really assembling a solid. It's not like in an optical lattice or anything anymore, where you would put single particles with unit filling on a lattice, but it's really a perfect crystal that is spontaneously forming because of the dipole-dipole interaction. So I guess that is the new kind of emergence that we were talking about yesterday. But the key question again is the dipole strong enough? Because we have learned, okay, dressing kills basically some of your microwave shielding, or also static field shielding kills some of your dipolar strength. The hard limit in the end, I guess, is the first field-linked resonance. You cannot go above this because you just get a lot of losses. So rather than this factor of 10 to the 4 that we always claim we're better than magnetic quantum gases, you end up maybe with a factor of 10 or 100, depending on the molecule you're working with. And so then the question is, can you reach these strongly correlated states or the beyond mean field regime? And this is basically what we looked at in this paper. I mean, this is a phase diagram that you can calculate. Okay, there's a gas, there's a transition to superfluid droplets, which I guess has already been seen. But then as you increase the strength, at some point you form these monolayer crystals. They're in a plane because these are antidipolar interactions from single frequency microwave dressing. The question is, can you reach something interesting here? And we've marked basically the location of the first field-linked state. And so that is good news in many ways, because first of all, you see that this region is sort of independent of this field-linked state, which tells you this is genuine many-body physics. This is not some two-body physics happening here. And then also, for high enough particle numbers, there's a region here where you can have that below the first resonance. And so you can reach this in experiment. What is actually saving you here is not like that you get super dense, but in the end, it's something that we've discussed yesterday. It's the shielding core. And as soon as this shielding core prevents your particles from getting any closer, then you basically split up into this state here, where the splitting is essentially the shielding core. Good. So can we reach these states? In this case, yes. But of course, one needs to investigate how this happens for more general situation. One also needs to investigate like why this is happening. This is Monte Carlo, and as we said yesterday, this is a black box. It's just coming out, but there's a fundamental understanding of like Li Wang-Yang corrections and so on is still missing, how this transitions. Well, you may also ask, this is actually what one referee asked, is there super solidity in this system now? And you can calculate the superfluid fraction and the crystalline weight, and you see, yeah, maybe there's some overlap here, but it needs more tunability in the end. Yeah, this is, I wouldn't claim that there's super solidity here, but there's hope, of course, if you have dual microwave dressing, for example, where you can now tune your parameters much more, that you can enlarge this region and then maybe see something like a super solid also in these weird crystals and kind of do this connection between helium physics and dipolar physics. Good, so this I'm going to skip. Yes, there's a lot of other nice pictures that you may have seen already that one can realize even if you're just in the mean field regime. So even if that doesn't work, there's still interesting stuff to do. And that's the people who did the work. Tatsam, for barium fluoride in particular, Tatsam is actually here, so talk to him. And also, if you like to dress up and party like it's 18 something, we have a postdoc position available in Vienna. So thank you very much for your attention.
We have time for questions. Yes. So the evolution of density in the progress from the superfluid to the supersolid brings to mind what looks like the attractor that forms in a self-organized criticality situation. I just mentioned that
Yeah, I
maybe
mean,
it talks
what I
to
can say is for sure understanding the nature of these transitions and what kind of criticality or what else may be happening across the phase transition is not so simple, because most of the simulations so far, and also experiments certainly, have been done in very finite size systems. And so actually getting to the bottom, I didn't read it out, but I think it was on my slide, like what's the nature of the phase transition that is happening here is not a trivial question. So it's interesting to investigate all of this, yes.
Question behind Anna first.
Very nice talk. One question is that for the calculations that you were doing, what is the role of dimensionality? So these were 3D, 2D.
Yeah, that's actually a very interesting point, because I mean, you start with something that is kind of 3D, and then it sort of has a I don't know if I can call it a phase transition, but it sort of switches into a 2D system, and that's something I'm not aware of is happening like anywhere else so far. Yeah, it becomes completely flat, which is actually very, very challenging for your Monte Carlo simulations in the end.
But you start 3D, so everything is
Yeah, I
flat.
mean, in the beginning, it's sort of 3D well, it's still like elongated in the 2D plane, but just because of the nature of the interaction and the isotropy. But at some point, it becomes perfectly flat. It's a monolayer crystal, so it's as 2D as you can get. Yeah.
And if you start very 2D, I mean, if you are able to confine tightly.
Yeah, this we have not investigated in detail. I mean, there's so many parameters that you can play with now, yes. But again, I stress, if you want to do Monte Carlo simulations of that kind, be careful, because, I mean, your Monte Carlo walk tries to escape this 2D plane, right? And it becomes energetically so costly that it gets stuck, essentially. So you have to be very careful when you do simulations for these systems.
I was wondering up to which point this crystal that you get there is basically a classical crystal with 0-point fluctuations on top. And whether you can get this boundary just from the Lindemann criterion for crystals.
We have not checked, but I would guess that it's a quantum thing, right? Because it's completely independent of this two-body bound state. So it must be something that at least involves all the particles. I would guess, of course, you're right, in the very far limit, I mean, you should end up with a classical Wigner crystal kind of thing, right?
But in this case, even if you don't have a two-body bound state, you may have that the presence of many neighbors basically is given to you a trapping potential. This is basically a 0-point. You can calculate the 0-point oscillations, and this will give you basically these blobs that you have there. And whether there is this so-called Lindemann criterion for the melting of the crystal, and I think that this must be basically.
Yeah, it could be
like boundary, so to say.
One should investigate. Like I was saying, I mean, it's very challenging to understand what the Monte Carlo really gives you, right? Because it's a black box, and these kind of things should be checked. But then even if it ends up being a classical crystal in like the far limit, the interesting part is, of course, the transition region in the end, because the classical limit you can understand, the normal droplets you can understand very well, and now the question is what is happening in between and how is it happening, right?
A great talk.
Thank you.
All right, maybe I have a very quick question. In the phase diagram that you had shown, does the droplet phase survive the thermodynamic limit?
So these simulations were actually done at a finite temperature already, and you can take this into account in the usual Monte Carlo algorithms. And so, I mean, the droplets have been seen, yeah. These were slightly different potentials than the ones that are present in the current experiments. But in principle, you can just put this in and they should survive, yes.
So there's a finite region even when n.
I believe so, yes. Yeah.
All right, let's thank Tim again for the talk.